All right, section 2.4 is going to move us beyond basic derivative rules to some that are a little bit more complicated. The first one we're going to encounter is the product rule, and the second one is the quotient rule. So the product rule, if it was like the basic rules that we had before, in particular that sum and difference one, the very last one, it would have the feature that if you multiplied f of x times g of x and then you took the derivative, that would be the same thing as taking the individual derivatives and multiplying them. That you could sort of do it in any order. Almost like an associative property or something like that, or a commutative property. This idea that this ordering doesn't matter. So the first thing I'd like to do is I would like to take a look at whether or not it really works. Okay? That's what everybody would like to be true. We would like this rule right here at the top to be the product rule. That'd be great. It'd be convenient. So what we're going to do is we're going to take an example and actually see if it works. So the example I'm going to use is I'm going to use that f of x is 4x to the 9th and g of x is x cubed. And we're going to do each side of that equation at the top. So the first side, the left-hand side, is taking the two functions and multiplying them together. And then after I do the multiplication, sort of an order of operations, moving to the outside of those brackets and then doing the derivative. All right, so what we're going to do is we're going to take function f of x, which is 4x to the 9th, the function g of x, which is x cubed. So working on the inside of the brackets, what is 4x to the 9th times x cubed? 4x to the 12th, very good. And then if I want to take the derivative of 4x to the 12th with the power rule from the last section, what would I get? 48x to the 11th. And that is, in fact, the derivative, because we did all the algebra first and we did the derivative second. That is for sure and certain the derivative of this product. What our question is could we have done the individual derivatives first, down here, and then multiplied them together and gotten the same result? So we're going to try that. So the first one was 4x to the 9th. What is the derivative of 4x to the 9th?
36x to the 8th.
Good, 36x to the 8th. What is the derivative of g of x, g prime of x, that is? I would get 3x squared. And what is 36x to the 8th times 3x squared? What is it? It is not 48, that is true. Does anybody have a value for it? I think it's bigger than 72, actually. 108, maybe? X to what power? X to the 10th. So even if it had the right coefficient, it for sure does not have the right exponent, right? What this does for us is it answers this question up here at the top. Does this work? The answer is no. This is not the product rule. This process cannot happen. I can't take the individual derivatives and simply multiply the product together when I'm done. Okay, so what in the world is the product rule then? Well, product rule actually looks like this instead. Okay, so you notice the left-hand side is exactly the same as the previous slide, right? You've got the individual product in the middle, you've got the derivative notation on the outside. But the way that we actually do the product rule is we take the first function and we rewrite it as is. No derivatives or anything, just rewritten. We multiply that by the derivative of the second function. And we do the exact same thing in reverse order. So now we take the derivative of the first function and we multiply that by the original of the second function. And this is a sum of those two features. So I want to show you that unlike the last one where it actually resulted in the wrong answer, this one actually works with the exact same functions that I did before. So before I used f of x equals 4x to the 9th and g of x equals x cubed, right? So this rule says I should be able to write down the f of x function, which is 4x to the 9th, and multiply that by the derivative of the g function. So what is the derivative of x cubed? 3x squared. Very good. To that we're going to add, so what is the derivative of the 4x to the 9th function, the first function? 36x to the 8th. and we multiply that by the original g function, which was x cubed. So we're going to simplify this. So what is 4x to the 9th times 3x squared? Good, 12x to the 11th. And then I've got a 36x to the what? 11th, and what are these combined to be? And that's exactly what it's supposed to be from over here, isn't it? Okay. Now, all of this is to show you that the rule works. It's not to show you that you actually have to do something two different ways every time you encounter one of these problems. That's not the point at all. But this is the correct approach to the product rule. This is the correct rule. So we do these individual pieces this way. I am not sure if your book has the product rule written in this order or not. Clearly, we could switch the two values here at the front with the two values at the back. We could just sort of turn the equation around because it's addition, right? Also, clearly, we could sort of switch the order of the f of x and the g primes. None of that would matter because it's multiplication. It's also commutative. I like this order, and the way I always think about this, the way I like to think about it is in this order because the first part of it is always something that I can just start with. All I have to do is just rewrite the first part of the function. And I kind of like the fact that I can always start the problem, even if I get messed up afterwards. I can always get the first piece done. So what I'd like for us to do is to take a couple of problems, and we're going to do this rule with them, simplify the results and so forth. As we continue to use product rule and the quotient rule later on too, they're going to become more complicated. So on this problem, obviously, we could simply just distribute everything and not use product rule, right? Yeah, I mean, we could definitely avoid using the product rule on this problem, but we're going to practice using the product rule so that we can see how that works. Is everybody good with that? Okay. So as you're working these problems, make sure that you're following the directions. This one actually says use the product rule. So you want to make sure you actually do it the way they intend for you to do the problem. All right, so we're going to find the derivative. The process in doing so is that I rewrite the first piece exactly as is. No changes. What's the next thing I do? Right, I'm going to find the derivative of this second piece right here. So what is the derivative of x squared minus 5? 2x. Okay. What's next? Do it the opposite way. So now I'm going to take the first function, which was the x squared plus 3, and I'm going to take its derivative. What's the derivative of x squared plus 3? 2x again. And then what am I going to do? I'm going to multiply it by the original second function, x squared minus 5. Now, next week on Tuesday, you have a quiz in class. Do you guys remember that? Have you sort of been paying attention to the schedule? The quiz in class next Monday is going to be on using derivative rules. Okay? If you were doing that quiz and you were doing this question, you would stop right here. You absolutely would not simplify a single thing in the problem. That's the point of that particular quiz. Okay? As you're working through your homework and when we get to the test, in most situations, unless you're otherwise told, you are going to simplify. You're going to clean everything up to the best of your abilities towards the end, combine what you can as you work through. Okay? So on this problem, we can definitely clean this up, provided we're not working on the quiz from next Monday or Tuesday. What is the first piece going to look like? How do I just clean this up right here?
2x cubed plus 6x.
Okay, 2x cubed plus 6x. How about the second piece? 2x cubed minus 10x. And then combining like terms, what do I get?
4x cubed minus 4x.
Perfect. Any questions on that one? Okay, we're going to do one that's a little bit more complicated. Are you ready? Okay, again, we could distribute this out and we could use power rules. That would be a way to do the problem that would be correct. But the directions ask us to use product rule, so that's the approach we're going to take on the problem. So as I'm taking a look at this one, what is my first step? Write the first one down. So x to the 3 halves minus 4x. What am I going to multiply this by?
3x. I mean 4x to the 3rd.
4x to the 3rd. Very good. The derivative of the second piece, which is 4x cubed. I'm going to do an addition sign next. This is the last difficult piece. That is the last piece where we're using calculus anyway. I need the derivative of the first set of parentheses. What's the derivative of x to the 3 halves?
X to the 1/2. Or, yeah, x to the 1/2.
Good. 3 halves, x to the 1/2. And then what?
Minus 4.
Minus the 4. So that's the derivative of the first function. And then what do I need to do? X to the 4th minus 2. This one's messier than the last one, right? The algebra to clean this one up is not quite so friendly. And we're working with exponents that are also fractions, which is making it a little bit more unfriendly as well. Let's take a look at what we have, though. So we're going to distribute this piece, right? So we have x to the 3 halves times 4x cubed. So there's going to be a 4 there. How am I going to combine x to the 3 halves and x cubed? You multiply them, and you do that by adding the exponent. So what is 3 halves plus 3? It's 4.5, which is 9 halves. Good. All right, the next piece then is minus, and I have the 4x times the 4x cubed, which is going to give me 16x to the 4th. Beautiful. The next piece over here is more complicated because it's a binomial times a binomial, right? I don't have a monomial times a binomial. So I have to FOIL, or at least that's one way of doing it. I'm going to distribute my first terms. What is 3 halves x to the 1/2 times x to the 4th? I'm going to get 3 halves. Then what am I going to get? That's x to the 9 halves again, isn't it? Because I've got 1/2 plus 4, 4.5 or 9 halves. My outer terms. So now I have 3 halves times x to the 1 times x to the 1/2 times the negative 2. What's that going to give me? Negative 6 over 2, which is negative 3. And then x to what? X to the 1/2, right. I think we're ready for our inside terms, right? Well, that's a nice one, isn't it? What do I get there? Negative 4x to the 4th. And then the last terms right here, what do I get? Plus 8. Is everybody good with the distribution? Some of these terms have common values that we can combine, right? So let's start with the first one. 4x to the 9 halves can combine with 3 halves x to the 9 halves. So what is 4 plus 3 halves? That is 11 halves. Very good. 11 halves x to the 9 halves, right? So in some sense, we've sort of taken care of these two pieces now. The next one is actually negative 16x to the 4th. And I have another x to the 4th over here. So how many x to the 4th do I have? Negative 20x to the 4th. And we've taken care of those two pieces. And then I have the other pieces that don't combine. So I've got negative 3x to the 1/2 and then plus 8. What's even interesting on this one is because of how we sort of processed through it, they're actually in order of descending exponents. Not that that really matters, but if you were to look in the back of the book, this is probably the order they would put it in because of that. So the 9 halves is a bigger exponent than the 4, which is a bigger exponent of the 1/2.
So whenever we're doing our quiz, it's just the second step is that you do.
Yeah, if you were doing this on your quiz, you could stop right here. No simplification needed. We're going to practice more for the quiz stuff later, I promise. But yes, there's no simplification on the quiz next week.
Is it like that for the entire thing? Like,
For the entire quiz?
yeah.
Mhm.
It's like you're not actually solving.
You're not simplifying anything, yes. Mhm. All right, we have another rule in this section called the quotient rule, so let's take a look at that. We're going to take a look at that in exactly the same way that we took a look at the product rule. Question, f of x over g of x and take the derivative, is it the same if we just take the derivative of the top and divide that by the derivative of the bottom? So what do you think? I'm seeing some heads shake no. I wish it were. That would be very intuitive, right? It would be very natural. It would feel like what we would expect to happen. So what we're going to do is we're going to try it out to show whether it does or does not work. So the same thing like we did last time, we're actually even using the same functions. So I'm going to take the 4x to the 9th as my top function and my x cubed as my bottom function. We're going to simplify that. So what is 4x to the 9th over x cubed? 4x to the 6th. And what is the derivative of 4x to the 6th? Excellent. Is everybody good with that? Oh, look, there it showed up. And this is the correct answer. This is correct. Done exactly right. This is the correct answer, okay? What we're trying to see is whether or not we could have done it and done the derivative pieces first and then divided second. That's the question here. So we're going to try that then. So what is the derivative of the 4x to the 9th? 36x to the 8th. And then what is the derivative of the x cubed? 3x squared. And then can we simplify that? What will it become? 12x to the 6th. And lo and behold, they don't match. So I can't just take the simple derivative of the top, simple derivative of the bottom, and call it good. It won't give me the correct answer. So again, does this work? And the answer is no. This is not the quotient rule. It does not work. This is unfortunate because the quotient rule is more detailed than this would have been. I wish this worked. It would be so much friendlier. So let me show you what the derivative rule actually is for the quotient rule. See? The top of that should look familiar. It's very much like the product rule, but there's one difference. They look like they're switched around in the order, but we talked about that with the product rule. The order didn't matter. The order matters here. Why? Because there's a subtraction sign, isn't there? So there's a subtraction sign on top, whereas the product rule would have had an addition sign on top. And now the order does matter, and you notice that it does look like it's actually flipped of the way that I presented the product rule. And then the denominator, we've got the denominator going on here too, where we've got the denominator squared, right? I'm not going to actually show you that this pans out like I did on the last one. I trust that you could actually work out those particular details. We're going to do some other examples with this. But what I do want to show you is I don't know if I would call it a mnemonic device exactly, but I want to show you the way that someone showed me when I first learned calculus how to remember the quotient rule. Okay? And there's several different variations of what I'm going to show you. So the one that I was taught was that we could call the numerator high and the denominator ho. Like hi ho, it's off to work we go. We have the 7 dwarfs. I've also seen variations where the denominator is called low, as in being high and low. Oh, that's fine. And so to this day, whenever I see a product or a quotient rule, this is what goes through my head. Ho-de high minus hi-de ho. All over ho-ho. Yes it is. This is what I always think of when I do derivatives of quotient rules, with quotient rules. So the denominator is what we've called ho. D high is the derivative of what's on top, d high. The original of what's on top, high, minus the derivative of what's on bottom, ho, all over the denominator squared. Ho ho, it's Santa Claus on bottom, right? Yeah. So, and if you have other versions of this, that's fantastic. Share amongst each other as you guys are working in groups. That'll be great. But it's just something to help you remember it in a less formalized way. That's all. So we're going to do some examples now with the quotient rule. Are you ready? All right, so here's our function. It's important to realize that unlike the product rule where I said, hey, look, you could have done this in a different way, right? We could have just multiplied everything out and it would have worked. And we could have used just regular, rules back from the last section and everything would be fine. I couldn't do that with this problem. This problem doesn't have the ability of simplifying down into such a way that just using power rules works. I have to use the quotient rule. I don't have an option here. So let's take a look at what we've got. We're going to take our g of x function, or g of t in this case, so g prime. And what we do is we do the denominator first. I take my denominator and I write it exactly as is on top. So 5t minus 3. And then I multiply by the derivative of the numerator. So what is the derivative of this numerator? 2t. And it's subtraction because I'm doing a quotient rule. And then I switch the order of this. So I write the numerator, t squared plus 4. And I multiply that by the derivative of the denominator, which is 5. Very good. All of this is written over the denominator squared. So if you were doing this on the quiz next week, you'd stop. You'd be done at that point. Cool? Believe it or not, you've done all the calculus there is to do in the whole problem. Everything else is algebra. Calculus is just really our way of getting you to be really, really good at algebra, because you do a lot of algebra in calculus. So we're going to simplify that numerator, yeah? So what does that simplify to, the first piece? 10t squared. And then what? Minus 6t. Excellent. And then some of you had some problems with remembering to distribute these negatives. You're working on a different situation, but you still had a negative issue. This negative distributes to everything inside. So do make sure that you get negatives on both pieces inside when we do this. And we're multiplying by the 5. So this is actually negative 5t squared and then negative 20. Is that okay with everybody? It's just an easy thing to overlook. And then I have the 5t minus 3 squared in the denominator. All right, numerator simplifies one more time to what?
5t squared minus 6t minus 20.
And it's over the denominator squared. Now, one thing to be aware of is that if we had the ability to simplify the numerator with the denominator, we would want to do so. This one does not have that ability, and I can see very quickly why. While I certainly could have a factor of a 5t at the beginning if I were to try and factor this, there's no way I can factor the 20 into having a factor of 3. Right? I couldn't ever get 5t minus 3 as a factor because 20 doesn't have a factor of 3 in it. So even if I were able to factor the numerator, it wouldn't reduce with what's in the denominator. So that's how I can actually know that I'm done on this problem and there's no simplifying to do. Any questions on this one? Okay. We have one more example here, direct example anyway, of the quotient rule. And I think it's worth noting on this one that if I weren't told to use the quotient rule, I could do something different on this problem. How does this problem differ from the last one? It does have a negative 2 on the side. The negative 2 on the side doesn't actually affect anything. There's something else, though, that makes it... There's a square root. That doesn't affect anything either.
It's split into fractions. You can do it as...
Yes. Blaine, do you know why I'm able to do that on this one and I wasn't able to do it on the last one?
Because there's the 5t minus 3.
Yes. All right, this denominator has subtraction in it. Do you guys see that? So while I could separate sort of the numerator divided by the denominator in each of these, I would still have the denominator as 5t minus 3, a whole bunch of stuff. I mean, an addition or subtraction in the denominator. So I would still be stuck using the quotient rule. On this one, if I wanted to, I could split this up into the individual fractions like we did in the last section, And I could actually work with it by taking that 5t, or that 5, sorry, it's an x in this one, that x squared up to the numerator. I could simplify each of the factors because I don't have addition and subtraction in the denominator. So I actually do have an option on this one. I'm not going to pursue that option because the directions tell me to use the quotient rule, right? So that's what I'm going to do. But I want you to be aware that there is another choice on this one that we could actually handle. Let me come back to one other thing that was mentioned here. The first thing you guys noticed is that this has the -2 out here at the end. What's the derivative of the -2?
0.
It's 0. So that -2 on the end is just going to fall out. It's not going to have anything to do with the rest of the problem because its derivative is 0. If this had said -2x or something like that, we would just take its derivative separately because it's not affected by or really interacting with the quotient at all. Okay? All right, so as we work this problem, we're going to do it with a quotient rule. And that -2 at the end is going to drop off in our very first step. So the first thing I'm supposed to do is I'm supposed to write the denominator as is. And then I'm supposed to take a derivative of the numerator. So what is the derivative of 3 minus 6 square root x? All right, so this is what you should sort of be thinking. The way you already answered the question, this 3 is going to go away, right? The derivative of the 3. This -6 is going to get multiplied by the 1/2, which is going to give me the 3 that you mentioned and the negative that Blaine mentioned because there's a negative on there. So this is -3. And then what's the exponent going to be on the x? It's going to be -1/2. Very good. And then I'm going to have subtraction because this is a quotient rule. What do I do next? I write the top part, and I'm going to write the top part in the exponential notation with the exponent of 1/2, because eventually I'm going to have to work to simplify these anyway, so it's kind of nice to have it written that way. And then what? Yeah, the derivative of the bottom. So what's the derivative of 5x squared? 10x. All of this is going to be written over the denominator, which is 5x squared squared. And we will simplify that in a moment because we're going to be able to clean this up a lot because of the nature of the problem. Okay then, so what's the first thing that I can do on the top to clean up? What do you see? And I don't even have to distribute on the first one, right? Because there's actually just one term in each of them. So you can just combine, right? So I have 5 times the -3. What is the x to the 2 times x to the -1/2? X to the 3/2. We're adding fractions, right? Add the exponents. So this is x to the 3/2. I do have to legitimately distribute though on the second one because I have a binomial 3 minus 6x squared. So this will actually be distributed. And this negative is going to distribute through here as well. So this is actually going to change this to a negative and this to a positive when I distribute this negative through. So the first sign is actually going to be negative. I have that 3 times the 10x to give me 30x. And then I have the 6 times the 10 to give me, and it's positive, 60. And this will be x to what power? 3/2. What's the denominator actually going to be? 25x to the 4th. All right, so somebody tell me something you're seeing. There's several things to see at this point. What are you seeing?
Simplify the top further.
We can simplify the top further. What would you like to combine, Taylor?
-15x and 60x.
Okay, so what is -15 plus 60? 45. So 45x to the 3/2 minus the 30x that's already there over 25x to the 4th.
They all have a factor of 5.
Good. All the coefficients have a factor of 5 in them, don't they? So we can actually reduce all those coefficients.
Can it be by 5x as well, because 45x to the 3/2?
Yes, that's the other thing we can do. Let me do the 5s first. I'll just write it on here, and then we'll do the x's second. So if I do 45 divided by 5, I get 9. 30 divided by 5 is 6, and 25 divided by 5 is 5. And then now, just like Blaine said, they actually all have a factor of x in them too, don't they? So this x to the 3/2 will become x to the 1/2. The simple x over here with the 6 will actually just go away. And this x to the 4th will become x to the 3rd. So the grand result of all this is that I have 9x to the 1/2 minus 6 over 5x cubed. No more simplifying, right? Nothing else we can combine or reduce. All right, one last problem in this section. How's this one different than the questions we've been answering already? S for a tangent line, which means the answer at the end is going to look like an equation of a line, right? So I have x, I have to find y, and I have to find a slope. What would you like to do first? You want to find y? Is that what I heard? Yeah, okay. All right, so yeah, we can find y. So how do we find y? Great, so we're going to plug in the number 1, because this says a equal 1, into our function. So if I plug that in, I get 1 plus 3 over 1 squared plus 1 for a grand result of what? 2. 4 over 2, which is 2. All right, so my x value is 1, my y value is 2. That's already a step ahead of the last section when I had 29/2, right? No fractions yet. All right, let's see what happens. Okay, so I've got the x value, I've got the y value. I need now to find the slope. How do I find the slope of this particular line that I'm looking for? I use the derivative, and in doing so, I'm going to need to use the quotient rule, right? All right, so quotient rule says I do what? All right, so I take the denominator, which was what we called g of x, times the numerator, which is what we called f of x's derivative. So what's the derivative of the top? 1. It's probably the nicest one we're going to run into all day, right? I don't know, actually 0 might have been better. And then I have a subtraction sign. And then what do I need? I need to write the numerator out this time, which is the x plus 3.
Oh, yeah.
All right, so we do the actual numerator. And then I'm going to multiply that by what? Careful. The derivative of the denominator, close. 2x, yeah. So we need the derivative of the denominator, that's the x squared plus 1. And the derivative of that's actually going to be 2x for us. Good, you guys are on track. And then I'm going to divide that by what? X squared plus 1 squared. Now I'm going to simplify this a little bit, but it's worth noting that if you wanted to simply plug in the value 1 everywhere, you could do that right now, right? Yeah. And that might be more practical in some particular problems than to actually simplify with the x's involved. This one's not too difficult, so I'm going to go ahead and simplify one more step with the x's. But I just want you to be realizing that if you had square roots and powers of weird stuff everywhere and you're putting in x equals 1, put it in. Because when we take square roots and cube roots and things of 1, they're still 1. I don't need to deal with all of that any longer. This one doesn't have any of that, so it simplifies really pretty cleanly without having to worry about it. I have x squared plus 1 when I distribute the number 1 there. And then I have minus 2x squared, and then again minus 6x over the x squared plus the 1 that was already there squared. And I'll go ahead and combine those x squareds on top. So what does that have? Give me
X squared minus 6x.
negative x squared first, right? And then minus the 6x plus the 1.
So how do you know when to factor the bottom and no?
You mean when to just
Boil.
like simplify the denominator? Very seldom is it helpful to actually multiply this out. Because the only thing that can possibly happen that's good in that is that it actually simplifies with something on top. And it's easier just to recognize that it's simplifying with something on top if it's in factored form. So very, very seldom will we actually simplify the denominator. The reason we did on this last one was because this denominator didn't have any addition or subtraction in it. That's the only reason it was helpful to do it in this one. right, can we evaluate this at x equal 1? You betcha. So what is this at x equal 1? I have negative 1 minus 6 plus 1 over 1 plus 1 squared. What do I get? Is it negative 3/2? I think that's right. I would have this 1 and this 1 cancel. That leaves me with negative 6. This is 2 squared, which is 4, and then I can reduce them both by a factor of 2. So this is my slope. All right, so let me kind of carve out a little bit of space right here in the middle. So I've got y minus the y value, which we found is 2, equals my slope, which is negative 3/2, times x minus my x value, which is 1. And if I'm asked to do so, that is to solve for y, I would then multiply and distribute and so forth. So I have negative 3/2 x plus 3/2. And then I'm going to add the 2 to the other side as well. So my equation is y equals negative 3/2 x plus what? Is it 7? Okay, thought I heard 9. I'm sorry. Yep, 7 negative. It's positive 7/2. So that's my equation of my tangent line. Let's say you wanted to make sure this was a realistic or a reasonable answer. What could you do? You could graph them. What would you want to graph, Ben? Yeah, the original f of x function right here, right? And what else? And then the tangent line that you just found, the y equals. And what would you be looking for? How would you assess, is this reasonable? We would see if it looks like it's actually a tangent line at the point x equal 1, right? If it looks reasonable at that point. Any questions on that? All right.